Hi, in this class we're going to explore some more advanced techniques in terms of distribution, population, likelihoods, probability, and integrate some noise in some more abstract ways to get more efficient or better results. So here we got a situation where we really want to work topology independent. What I have here is I have some very, very basic geometry that I have no desire to subdivide and remesh and that sort of thing. It's really just like very bare bones basic geometry. And then here I've got a ocean, and we want to populate these barnacles. We want to have an automatic barnacle population system that will automatically detect where the ocean surface is and where these poles are, and make us some nice patterns with some relevant particle scales and some rotations and whatnot. So how would we really go about that in Houdini? So I'm going to go ahead and I'm going to copy these starting points from the scene, the poles, the ocean, and the barnacle. And let's get started. Okay, so the first thing I want to do is I want to get the entire region of where these barnacles would be populated, because the wonderful thing about scattering is that it's fairly resolution independent and very efficient as well. So even if we get a little bit more points than we need, it's generally considered a really efficient process. So we could just scatter based on the surface here, and turning off relax and forcing the count. But here's the problem, is that we're kind of limited by the actual scene topology that we're dealing with. And here it's still pretty like lo-fi topology. I want to take a little bit more control over the positioning and how far apart these things are spread. So for that, I'm going to go to volumes. So I'm going to do a VDB from polygons. And here, I'm able to generate some distance VDBs. I'm just going to turn that to a fog VDB. And if we were to just scatter based on that, now we've got some volume, which is better to work with. But what I really want is I want to push this out a little bit. I don't have any need for barnacles inside of the surface. So for that, I'm going to use a peak sop. It's very simple geometry, so we can take advantage of that. So I'm just going to push this out using the normals of the geometry. So the peak sop works on either implied or explicit normals to push point positions around. So here we're able to push that around, and we can set whatever distance we'd like from the surface. And I'm also going to make a VDB out of that as well. So we've got this VDB and we've got this VDB. And now I'm just going to subtract one from the other. So VDB combine. Whenever geometry just really doesn't work or breaks down, volumes are always a good option. So I want to take the bigger one, and I want to subtract the smaller one from it. So I'm going to subtract these from each other here. There we go. So now we should have kind of a hollowed out area in these VDBs, and scattering on that, we should be able to observe some space in the middle there. So we can kind of procedurally control how far from the surface. Now let's up this density a bit. So with scattering, I tend to work in exponents. So here, let's push that a little bit. Here I'm going to do a density of 1,000. And what the other reason to work in density when scattering is that if we were to add or subtract a pole, we wouldn't be having more or less density and thus changing the look of our effect. So adding a more pole, we create more area, and we still maintain the same density, so we get the same distribution of points. All right. So we got these points, and now I just want to only keep them when they are pretty close to this ocean surface. Well, the first thing we should definitely do is time shift the ocean surface to where it's no longer moving, because we really just need it to be close to the surface. We don't need it to be exact. So I'm going to lock the frame to F start, and this will take out the time dependency, because gathering a distance can be a fairly intensive operation. We don't want the barnacles to be appearing and disappearing either. Okay, but we have another problem, and that's the fact that previously, when we had scattered some points, we were using an attribute on the surface to roughly control the distribution. Well, due to this operation, we really can't go backwards and try to figure out where these attributes should be. That's going to be a lot of work, even if we can do it at all. So what's really powerful is to be able to take an existing point cloud and cull it and do percentages based on different factors. I want only the points that are closest to the water, and as they get farther away from the water, we have less and less points. Okay, how do we do that? So starting with the point VOP, our vector powerhouse, we're going to query all of these points, and it helps that VOPS is very fast for this. We're going to query what their closest position is to this surface. Now, if we had huge resolution differences here, then we could also scatter on this surface as well. In fact, I'm going to do that right now. Okay, and this is a great way to work in a truly resolution independent way. Okay, that's probably going to be a bit too many points, but this is not necessary. But yeah, here we're working in a truly resolution independent way. I'm pretty confident that it's going to be able to find pretty even distances throughout. So we're going to compare this point cloud to this point cloud. Okay, and note that the first input of a VOP is what is going to be processed. So we want to plug the fluid surface points into the second input. Okay, diving in. There's a really valuable little VOP called near point. It's not as fast as, say, a point cloud lookup, but it's still pretty fast. And here I'm going to gather the nearest point in the second input based on my current position. And just spitting that out into the color, automatically we'll see that we've gathered all of these point numbers, which seemingly don't matter too much, except that from these point numbers, we can gather the position of that point or any attribute we want off of this. So here I'm going to do a get attribute. Okay, using this point number, I'm going to get the position off of the same input. And now if we want to just test that out, see, we've gone to all of their nearest point positions. So we're well on our way. From this, we want to find the distance. That's easy. We've got a distance VOP. So I'm going to take the current position, which is still this, and I'm just going to find the distance with this VOP. Testing that out in the color, you can see you've got little black spots around where the surface would be, the surface of the fluid would be. Okay, and that means it's a distance of 0. And as it goes up, it gets higher and higher. Well, I want to do something with that distance. So now let's use a fit. So the only real variable is how far away do we want it to go. So that's where we go from 0, which we know the minimum distance is 0, to the maximum. That's what we don't know. We want to be able to adjust that. So I'm going to make that a parameter in our top level network here. So clicking on that, let's call this maximum dist, max dist. Something that is easy to conceptualize. And now we can see that as we adjust this max dist, we can make our distance more or less relative, like that. And then finally, I want to be able to control this value. I want the most in here, not the most up here. So I'm going to do a ramp. And a ramp is allowing us to remap that to our desired range. So I'll call that curve. And now we can really work with this. Just because this can be a bit slow, I'm going to say on mouse up. And now we'll see the updates once we release the mouse. Okay. I'm going to here's an easy way to get the distance, is to make a pretty harsh fall off. And then when I get my desired distance, I'm going to view these poles and the ocean here. And let's get our maximum desired distance first. Let's say that's around 6. And now I want to adjust the fall off a little bit. Okay, so it's concentrated in here, and then it's going to fall off rather quickly as it goes down to here. All right, well, we've got this color value, which doesn't do us any good. Let's use this color value for something. Okay. So what I'm going to do is we're going to use this to either keep or delete a point. Now, if we just said if you're greater than 0.5 or greater than 0.6, all we get is a harsh cutoff. I want a likelihood. I want to say, are you more likely or less likely to be deleted or kept? So for that, for any likelihood, we need a random number. All right, so that's where the random comes in. So here I'm going to get the random, and we're going to base that off of the only thing that's different from point to point, which is the point number. And now we have our completely random value. So here's a random collection of lights and darks, high and low values. Here is the ordered collection of high and low values. And you might be following already, but here, the next step is I'm going to compare these two things. I'm going to say, if you're higher than the random, then be kept in here. If you're lower than the random, which is likely out here, then be deleted. So we're going to do a compare. Here's how that will work. If our curve is greater than the random number, then not, switching the 1 with the 0 here, the true with the false, not delete. And the way to delete is by remove point. Okay, so we have to feed the point number into the remove point. So for here, we'll do a two-way switch. So not use the current point number, which is point num, or use -1, which actually is not a valid point number, so that won't cause a deletion. And we'll feed that into the point number. And now we've done a procedural keep or delete operation. Because we might want to do more stuff with this valuable data, we want this to live past this delete operation. So the valuable data is actually out of this curve. After that, it's a fairly random thing, and it doesn't matter because it doesn't, if it gets deleted, then it's not there anyway. So we want the data out of this curve. So for that, I'm just going to export a parameter, and let's call this rel, and that's just a keyword I use for size, relative size. Okay, so I'm just going to export that, and now I know kind of like what its distance from the surface was. So I might want to use that for the scale of the barnacle later. Biggest ones in here, smallest ones out here. Okay, so we're halfway there. We have a collection of barnacles. We can control how far outwards they are with our peak. So maybe I want to dial that up a little bit. It's a fairly efficient, non-time dependent operation, and also, most importantly, non-topology dependent operation. You can scatter these barnacles on anything that's close to the water. Well, now I want some variation in here. So that's where I'm going to use a scatter on the inside barnacles. This area. Well, I'll use the same density of scatter here. Just so I know that it's the same density, I'm just going to copy this parameter and paste that into here. Okay, and I want to get the distance of these guys from this. And by doing that, we'll be able to get a similar gradient. Here we've gotten a gradient from the distance of the water surface, and now I want a distance of how far outwards this barnacle is. So we can actually just copy the same setup we've already done. We'll call this dist from water. Let's call this dist from pole. And just so it doesn't have to process as much, I'm going to plug this into here. And I'm going to set the max distance to a lot less. In fact, we can even set the maximum distance to our peak value. Okay, and now we see that if it's really close to these points, it's white, and the farther away it gets, the more dark it is. Okay. However, we've overwritten our rel value, so I don't want to do that. I actually want to add this thing, I want to integrate this thing into the existing rel value. So I'm going to read in the rel value coming out of here, and I'm going to multiply that by our current value. So in comes the rel attribute, and they're all high or low values out of here. And then we're just going to multiply this by this curve. And let's preview this in the color. And now we see we have both a gradient from the water surface and also outwards from our tube. I'm just going to make that a little bit deeper just to show. Maybe 0.6. There we go. Okay, and now let's get creative with this. So we can distort the position going into our system, and we'll be able to create results, because nature is not really a very even thing. It has all kinds of variation that might be present in it. So taking this very evenly distributed scatter, we could add a noise to that. Here we're dealing directly with positions. It's just a lot more efficient than always being tied to geometry as we work and topology as we work. Here, we're just moving points around, and that's a very fast, efficient operation. Let's add some AA flow noise to the position, and make sure to change your AA flow noise to 3D before plugging that in. And now we've got some varied positions, and we can just sculpt our noise with whatever noise pattern you like. Here I'm going to sculpt this by turning down the roughness. I'm going to adjust the frequency. It's actually not looking too bad from here. Let's test that out a little bit. Okay, maybe increase the amplitude. And now dial back in the roughness. Okay, so say I want that for my positional variation. And now what that's done is it's given us some variation as far as what's being kept and what's deleted off our original point cloud here. So now we have a much more varied look. The other thing I want to do is I want to go outwards from the pole. And for that, we can get a vector from our collection of near points outwards. Here's our current position, and we can say, how far away are you from this to that? And get a vector there. So also in this VOP, let's just get a positional vector. Here's our current position. And the way to get something that's looking to or away from another location, we're going to subtract. So here's the current position, and here is the nearest point's position. And if we plug that into the normal, which is the copy direction, now we're going to see we have vectors outwards. Here, let's visualize that at 1 just to see it a little better. Yeah, we have some nice directions outwards from the surface now. Okay, and here, just so that it's not affected by how far away it is and all that, we can normalize that vector. Okay, so now we have some nice vectors outwards from the surface as well. And they're varied because there's noise on these nearest positions. Okay. Finally, let's put some sizes on these points and then do our copy. So for that, it's just a matter of turning this relative value into a point scale, a p-scale attribute. So from here, in comes our rel, meaning the high and dark regions. It really represents the likelihood it was to be kept is what that means, the white and dark values. Okay, so in comes the rel. And we just want to fit that to our desired minimum and maximum p-scale. So promote parameter. We'll call this min and max. And let's export this to p-scale. Export when input is connected. Invisible. There we go. And we can see that we've got some really big spheres and some small ones. And if you aren't seeing those, just go to Geometry and Display as Disks. Okay, so now let's work with this a little bit. If any of these extra parameters are showing up, just say invisible. There we go. Okay, so let's get our very, very minimum barnacle size here. So I'm just gonna copy those together. What looks good? It's a bit small. Okay, and then get the maximum barnacle size. Working with points directly is so much more efficient than trying to deal with topology and geometry and polygons. Point clouds are incredibly powerful. There we go. All right, and let's try out our copy. So now I'm going to copy a barnacle onto this. Make sure before you do any intensive operation that you save. All right, so copy to points. We have our normal and our p-scale. And I'm going to go ahead and say pack an instance on the copy to points. And what that's going to do is it's going to make sure that each of these barnacles is not represented as its full geometry. And thus it's very efficient. Okay. And let's make that a little bigger. There we are. And we can see from here that we're able to really quickly and efficiently take control of our setups. We're not doing expensive remeshing and geometric cooks. Here we're able to change dimensions pretty readily. This would be a little thicker, but just to demonstrate. Yeah. And really take control of our scene population directly. This can lead into a lot of scattering and impact-based effects, lots of customizable fracturing techniques, so many different instances, whether it's like sparks, particles, crowds, or sourcing. Thanks, and I hope we learned a little bit about how to work efficiently with point clouds and population.